Yeah, I think we can get started. So it's my honor to introduce Joseph Falson for this condensed matter seminar today. He took the long trip from Caltech and is jet lagged and everything, of course. But we're happy to have you here. So I know Joseph Falson since a few years. But he started his career all the way back in Australia, and then meandered, I guess, his life all over the globe until he arrived in the US. So he did his PhD at the University of Tokyo, and then did some postdoc in Germany where I had the honor to meet you. And then now is an assistant professor at Caltech, William Hurt Scholar, Moore Fellow, and does fantastic work on epitaxy and low temperature physics, high magnetic field physics. We're very much looking forward to your talk. Without further ado,
thank you. Thank you very much. It's really fantastic to be here. I've known Matthias since we were both students. So, it's great. I was due to come in May and I had to delay that. I'm sorry, but I'm very happy to be here now. I'm sorry I omitted my title from the slide. When you're setting up a lab, you're kind of, living day to day when it comes to new data coming in. So I didn't want to be a little bit, too exclusive with what I was going to show today. So I want to show you the state of the art that's coming out of my lab. My department is applied physics and material science at Caltech. This suits my style of research very much. Most of my time and energy and money goes into developing materials. And ultimately what we want to do is study their physics at low temperatures. So I'm interested in not so much the applied properties, but fundamental physics of the electronic structure of crystalline materials. So I want to start just by zooming out and thinking, where are we now in the field of quantum matter, and what degrees of freedom are important to us, and maybe what lies ahead. And I was thinking about these things when I was setting up a lab in terms and trying to parameterize what type of problems we want to work on. So I've set up just this 2x2 little array of examples of where the lattice plays a key role in deciding the physics of quantum materials or quantum matter. A traditional way of thinking about quantum wells, which still rings true, is the idea that if you have lattice commensurability and chemical compatibility, you can make these type of complex heterostructures. This is some form of perovskite, right? And you can grow these heteroepitaxial layers, and if the lattice matching is good, then they'll hold each other together, and you can engineer interfacial physics through these means. So this is a very well-studied state or convention. And on the other diagonal over here, this is the idea which has emerged in the field in the past few years, where we can throw away this conventional way of thinking about interfaces and make these artificial interfaces with these emergent periodicities. And these emergent periodicities really breed new band structures and modify the interaction effects, right? And this is, a very, from the point of view of epitaxy, a very unconventional way to think about these interfaces. Now, I would say on these off diagonals here, there's something kind of gray in the middle. And this is where you have either ultra-thin materials, which go on an interface and are kind of held together in a weird way, or you take a 3D material and you reduce the dimensionality. So this was the case with nicolates, which were shown to be superconducting when you take it from a 3-dimensional perovskite phase to a 2-dimensional lattice, which kind of looks like a cuprate. And then this is, of course, the famous example of iron selenide, which as a bulk crystal is superconducting, but when you make it monolayer epitaxially, the TC goes up by an order of magnitude. So there are tricks that substrates can play which go beyond just making quantum wells. There's kind of subtle interfacial physics that the substrate can induce. And this is what I wanted to explore in my lab. So I'll say that this kind of ignores the traditional rules. So the first 40% of this talk will be fairly heavy on materials, just to show you what we develop, and then I'll transition later on into a more physics-like theme. But I wanted to introduce the tool that we use and some special tricks that we've built into the lab. So this is just a photograph of part of the lab. These are ultra-high vacuum deposition chambers connected to a glove box. And basically, the idea is that in thin film epitaxy, we take this high vacuum chamber and we evaporate stuff onto the surface of substrate, which we can choose from commercial vendors, which is based on the lattice constants, the lattice symmetries, the surface energies, these type of things. And we deposit the materials that we want on the front side, and we do this at an elevated temperature, and we synthesize them. So this is deposition, but it's also crystal growth. We're trying to change the phase on the surface. Okay, and most of the periodic table we can access. Now, maybe not all at once, but technically speaking, this approach can access more or less the whole periodic table. Usually this substrate is heated by basically a light bulb, which has certain limitations. And one of those limitations that we wanted to overcome was related to temperature. And to do this, you could look back in the literature to the 90s or even earlier, but this is just a nice picture that I took from a paper in 1997, where here they were doing pulse laser deposition, which is kind of a cousin of molecular beam epitaxy, and you have some substrate here, and you're depositing something on the surface. In this case, it was Ti203, and they were heating the substrate here with a long wavelength laser. So this is an infrared laser, a 10 micron CO2 laser. This is an industrial high-powered laser, not a scientific laser. Okay, and what's really convenient is if you look at the transmittance of, for example, sapphire, you have band transitions at short wavelengths from the valence band to conduction band. But if you go to very long wavelengths, you start to push this light directly into phonons. So these oxides, or generally speaking, ionic solids, tend to absorb very strongly at 10 microns. So this is a way to directly inject heat into these substrates. And in a modern sense, this was re-engineered by the group of Jochen Mannhardt and Max Planck when I was a postdoc there, taking the same CO2 laser and doing some beam shaping in a slightly more sophisticated way. And what you do is you take the Gaussian beam and you turn it into a quasi-flat top in some free space beam profile, and you shine this on the back of the substrate. Okay, it's really not that technical. These are industrial tools. You can go to an industrial company and you can say, I want this. So a Caltech undergrad built this for me. And it's not as scary as it sounds. The alignment's a little bit scary. You have to, you burn holes in things to align this, and you study the burn mark. Anyway, what's really nice about this is you can just hit the substrate. This is a photograph of the bottom of the substrate holder with sapphire at about 2000 degrees Celsius, and you can see the substrate holder is quite cool. And one of the ways that we calibrate the thermometry is by melting sapphires. It's like over 2000 degrees. So this is using about 20% of the laser output. So you're really limited by the melting temperature of your material and not the optics or the laser whatsoever. So you have this immense window for growth now. And there's many degrees of freedom that exist, but we haven't got to them yet. So let me now talk a little bit about how magnificent sapphire is. For those who don't know, sapphire is like the best oxide substrate that we have. It's made in massive commercial quantities. It's extremely hard. It's very highly crystalline. It's extremely cheap. You can get big wafers. It's everything that you want in a substrate. And it couples very strongly with CO2 light, as you can see. So we can do these type of tricks. We can take an as-received substrate, which is flat. The z-axis here is maybe a couple of nanometers. But from somebody who studies crystal growth, this is a very ugly surface. There's no crystallographic details here whatsoever. And if you want to study 2D materials on these type of surfaces, you can imagine that 1 or 2 nanometers of roughness is going to cause troubles for you later on. So we can go to very high temperatures and we can let thermodynamics do the hard work for us with this laser heating system. So this is a substrate that's held at 1500 C for about 10 minutes, and then progressively higher temperatures, and you can see in these AFM scans we start to get these beautiful step terraces. This is all done in ultra-high vacuum, extremely fast, and extremely reproducibly. And by going to higher temperatures, you can do things like controlling step punching. So now this is 2 monolayers as opposed to 1 monolayer. Okay, and this works for a range of different substrates. Okay, so we can go to really high temperatures with this laser. And what I'd first like to demonstrate as the first material that I will talk about before talking about 2D materials is a very unconventional growth pathway that we discovered. I think that this is actually at work in a number of materials, but it's very hard to put a finger on and really identify that it's at play, especially with sapphire as a substrate. Okay, and so the title of this slide is Oxide Sans Oxygen, so growing oxides without oxygen, which sounds a little bit strange. So for somebody who synthesizes oxides, you will probably recognize this type of diagram. It's called an Ellingham diagram. And this describes the phase equilibrium between some oxidation state of some metal and other oxidation states in the partial pressure of oxygen versus the temperature parameter space. Okay? So basically, if I look at this black line here, I can say that on the left-hand side, aluminum would be 0+, so you would get metal. And on the right-hand side, I would get Al2O3. This is all that it's saying. And this is just entropy. This is just bonding. This is energy and entropy, right? The idea is if I go to really high temperatures, it would prefer to evolve gas and become high entropy, whereas if I go to low temperature, it's happy to be the oxide. And then, of course, increasing oxygen makes it more oxidized. So this is very conventional thermodynamics. And for every element in the periodic table, an Ellingham diagram exists. So this is aluminum, titanium, niobium, tantalum, so on and so forth. So it's just something you can drive around the parameter space with. So this is some partial pressure of oxygen, which you may think you could open a valve on your chamber and inject oxygen, and that's true. But we found there's other ways to get oxygen into this crystal growth pathway. And this is through what we think is diffusion. Now, diffusion, again, is not something particularly exotic, but it's not something you think about very often when you're dealing with sapphire, because the diffusion coefficient here of sapphire is very, very low. So if you look at a characteristic length scale, which I put on the right-hand side here, at something like 1500 C, your characteristic length scale of diffusion is maybe 1 angstrom per second. So it's a very slow process that this diffusion goes by. So if you're growing at 1,000 degrees or 500 degrees or something, this is going to be many, many, many orders of magnitude smaller. You're never going to see the effects of diffusion. But we can grow films at exceeding 1,000 degrees, and this is where we think that we can see diffusion of oxygen come in and actually compete with this partial pressure of oxygen that you expect from bulk thermodynamics. So let me illustrate that with a simple system with the titanium oxygen system. You probably know of titanium metal, I hope, and you probably know that titanium oxide is TiO2, which is a band insulator. It turns out the titanium system is very rich. There's a lot of oxides in the middle, and they have actually very interesting physics. A lot of them superconduct. Some of them are Mott insulators. There's a lot of physics in titanium. So this is the crystal structure of 4 phases. There's titanium metal, Ti2O, so this is titanium 1+, TiO, titanium 2+, Ti2O3, titanium 3+. Okay. So I'm going to try to replicate an Ellingham diagram over here experimentally. And I can illustrate that by staying at low temperature, for example, and then increasing the oxygen gas that I inject into my chamber. And I can see that I go from titanium metal to TiO to Ti2O3, which is exactly what you expect. Right? You're increasing oxidation by injecting oxygen. Fine. So this is gas control, this is conventional. Well, what we found is when we start to go above 1,000 degrees, we can mirror this phase diagram even in the absence of oxygen in the chamber. So to illustrate this, just look at this horizontal row here. This is at the base pressure of the chamber where oxygen is non-detectable. And we can go from titanium metal to Ti2O to TiO to Ti2O3. So this is making oxides in ultra-high vacuum just by growing at really high temperatures. So the only culprit that we can come up with easily is thinking that this is oxygen coming from the sapphire. And if you compare length scales with growth rates, it kind of matches. But what's really nice about this is actually these films grown in ultra-high vacuum have superior purity to those grown in oxygen. And this is 2 ways of illustrating this. This is X-ray diffraction, and on the right-hand side, this is resistivity. So, for example, if I compare, these are all for the titanium 203 phase. This is the Ti2O3 diffraction spot running down the middle here. And I can see for 400 degrees, even though it's phase pure, this is a fairly weak intensity diffraction, and there's no fringes, interference fringes on the side. Whereas grown in ultra-high vacuum at really high temperatures, we can see that this is a very beautiful, intense diffraction. And also, it is the strongest of the Mott insulating phases. So I have a lot more data to illustrate this point, but I'm going to just show you that the electron microscopy is also really spectacular. There's no macroscopic defects to be found whatsoever, and this is in spite of an 8% lattice mismatch. So all of the defects are located at the interface, and the electronic structure of this material is superior. So we call this diffusion-enabled or diffusion-enhanced epitaxy. I don't know if the community is going to agree with that, but the proof is there that it works. And the question is, where else on the periodic table can this work? And this is what we're exploring at the moment. So this is just a color rendition, basically, where these two colors indicate, on the left-hand side, this half box indicates how easy it is to oxidize the crystal. So if it's deep green, it really loves oxygen. Okay, and then on the right-hand side, this is how volatile the material is. So if you want to grow at really high temperatures, you can't have something that is volatile. It has to stick on the surface. So if I have green on both sides, or green and blue on both sides, I would say that this could work quite well for oxides going forward. And it looks like this part of the periodic table seems to be most promising. So we have titanium, it works very well with. Niobium, it kind of works okay with. Tantalum, it kind of works okay with. We'd like to try these other elements soon. So this is very exciting for us. I think there's a lot of opportunities to explore this new growth mechanism. So that's party trick number one of the laser, just going to really high temperatures. And now let me transition to the more physics-oriented part of my presentation, which is going to be talking about intermetallics. These intermetallics I will introduce in just a moment, but to just plot some names up here of various intermetallics that are of interest to our group, and then compare them to the lattice constants of commercial substrates. This is what thin film people like to do. They like to show that we have all these choices. And if you're working with perovskites, you tend to have a lot of choices. Unfortunately, these intermetallics tend to have relatively large lattice constants of about 4.2 angstrom up to about 4.6. There's not that many commercial substrates in this area, but we've identified magnesium oxide as a very useful substrate for these experiments, and TiO2 for fewer cases. But magnesium oxide has really proved to be our workhorse as a substrate. And this is another ionic crystal, couples very strongly to the CO2 laser, and we can make these beautiful atomic terraces of MgO. And for those who don't know, magnesium oxide is usually a pretty bad substrate. It's very hygroscopic, so it absorbs a lot of water on the surface. Dissolving that is quite difficult, and it has twins as well. But, a lot of these issues can be solved with a laser. Okay, so these chemical formulas that I put up a moment ago generally belong to this so-called square net structural motif. And this is a motif that I'll be discussing from now on. Now, painting in very broad strokes, this square net motif is named that way because there are covalent sheets of square coordinated elements here, and they are sandwiched between some ionic layer of some other element and an element here, and these are ionic, and not all the time, but generally speaking, considered to be less important to the conductivity. So you can kind of think about this as like a square version of graphene with stuff in the middle. But this is really the equilibrium crystal structure. This is what the chemistry gives you. These can be binary or ternary, MX and Z here, and you can see basically all of the periodic table has a color here, so it's a very versatile structure chemically. You can put a whole bunch of things in here and tune magnetic structures, superconductivity, a lot of different things. The red squares are the elements that I'll be talking about. From this chemical versatility and also the structural anisotropy, so maybe I'll mention here, this is generally somewhere in the middle of being a covalent versus van der Waals crystal. So some of them can be exfoliated, not all of them. And this is kind of going back to my very first slide about what can epitaxy do for us. One of the reasons why I thought this motif was interesting is because it is not true van der Waals. It may actually interact with the substrate in kind of an interesting way, because it has some bonding tendency in the Z direction. Okay, here's some best hits, greatest hits of this structural motif. The arsenides, these ion-based superconductors, as you tune the amount of electrons per ion atom through chemical substitution, you can tune the ground state from a spin density wave to superconductors on both sides. Right? This is kind of very similar to the cuprates, and maybe you could even put the cuprates in this family. In certain situations, like silicon zirconium sulfide, you can get these very nice Dirac crossings at the chemical potential with very little contamination of other bands. And then here we have cerium, rhodium arsenide. This is a very unconventional superconductor which lacks inversion symmetry about the cerium site and apparently has this type of change in the order parameter of the superconducting phase at very low temperature. Okay? So there's a lot of physics to be had here. So we first grew tellurides. Unfortunately, the physics here was really boring, but the structure was beautiful, so I kind of have to show it. So this is a dysprosium ditelluride, which when you have 3 tellurium here is a really nice metal, but with 2 tellurium it's a semiconductor, and for reasons, if you're interested, I can explain why we can't get 3 tellurium there. But the structural motif, at least, we demonstrated that it grows quite nicely epitaxially. Like, this is quite beautiful. It wets the interface very nicely. There's very few dislocations. There's very few defects to be found here. We can map out the elements, right? The problem with these dysprosium films is that the tellurium really is too volatile. Tellurium evaporates at about 250 degrees. We grow these films at about 400. It's really hard to dose tellurium in and keep the crystal stoichiometric. So what happens is it grows, it's progressively losing tellurium. And what happens is instead of forming a perfect square net that you'd expect, which would give you a metal, it forms this rotated root 5 by root 5, rotated 26 degrees, superlattice, which we can detect in diffraction. And this modifies the band structure significant enough so that we get this very strong semiconductor. But at least as a proof of concept that these crystals grow, we were very excited. But unfortunately, thermodynamics here works against you and breeds this tellurium deficiency. So let's now work on a crystal that thermodynamics works for you. And that's going one to the left of tellurium and going to antimony. The structural motif is basically the same. The slight details are different that I'll speak about in a moment, but we have lanthanum and antimony ionic layers and then antimony square sheets. This is nice. We have an orthorhombic crystal, so there's a slight difference between A and B of some percent, and it's a big unit cell out of plane. Okay, and then if you're used to looking at phase diagrams, this is something that you really want to see. This is what we call a line compound. Line compounds traditionally grow as beautiful crystals because thermodynamics doesn't allow them to be off stoichiometric. So instead of being off stoichiometric, they'll form other phases. So if you can stabilize this phase, it will be high purity. And this is the case for gallium arsenide, for example. It's really the core of the reason why gallium arsenide is so highly pure. Okay. So thermodynamics should help us here, and lanthanum is antimony is less volatile than tellurium. Okay. So let me now talk about why this material is of interest from a physics standpoint. There are a lot of general features associated with the band structure which could be tantalizing. Whether or not you can realize them is a completely different story, but there's a lot of band crossing quite close to the chemical potential, so there might be some topological features here. Okay. If you look at not lanthanum, but if you look at cerium on the right-hand side, which is the same structure, this material turns superconducting under pressure. So this is 3 gigapascal, and it turns superconducting. Okay, and this superconductivity is concomitant to the suppression of antiferromagnetic ordering. So this looks like a quantum critical point. Okay. And then in lanthanum antimony, there is kind of similar features as well, where forgive, this data is not very nice to look at, but it's the best that's available in the literature, where pressure is plotted on the horizontal axis and temperature on the vertical axis. And these green and blue dots correspond to some discontinuity in the resistance, indicating like a charge density wave or a structural phase transition or something like that. So that is suppressed, and then superconductivity is enhanced. So this is very much like quantum critical point physics in both of these scenarios, maybe with slightly different flavor in the details. Okay. But these both happen under pressure. And the question was, does epitaxy give us pressure? Right? We know that we can, or we might be able to grow these films, and what does the substrate do for us? So one of the tricky points here is that even though people have studied the electronic structure of these materials under pressure, nobody has reported a crystal structure. High pressure crystallography is difficult. I haven't done this, but it's been described to me as taking a piece of paper, doing it, and then saying, tell me what is the structure. I don't know if that's true, but this is how it's been described. So that's kind of a hindrance, but it is what it is. Okay, so one of the reasons why this, for example, this discontinuity here, or these alpha or beta phases may be a structural feature, is because if you go across the rare earth row, you can identify at least 3 different what we call structure types in this material. Now, structure types are just a crystallography term for identifying basically how the atoms coordinate. Okay, there's many structure types in existence, and in this family of materials, there's 3 identified thus far. On the left-hand side of the rare earths, you get this samarium type structure type. In the middle, you get europium, and then on the right-hand side, you get ytterbium. Okay, so this is characterized in bulk. It's a little bit weird to look at in this representation, so perhaps I can give you a representation that is a little bit more intuitive. We can take our unit cell and we can chop it into quintuple layers, so these little building blocks here. And I can have a displacement vector and I can move them around relative to each other, and I just stack them up like this, and I ask, where is my energy minimum? This is basically what it's saying. And these are energy minimum maps, basically saying if I have a displacement in X and a displacement in Y, and I repeat this motif, how does my crystal build up? Okay, and for samarium, this is the energy minimum here, so this corresponds to a quarter unit cell displacement in X and in Y. So that's just showing this diagonal displacement between quintuple layers, whereas ytterbium prefers to be up-down like this. So this is the energy minimum up here. So samarium goes on the diagonal, ytterbium goes on the up-down like this. So this is kind of the way that you think about this stacking. And this is thermodynamically driven. Okay, so this is where we are in terms of understanding the crystallography of the bulk. So we grew these films. I'll show you some more diffraction in electron microscopy in a moment. But this is out of plane Bragg diffraction. And they're single phase, we see 006, 8, so on and so forth. There's no other phases to be seen. But you can see that the 006 diffraction spot is really significantly offset from the bulk diffraction condition. And this corresponds to about a 5% contraction in the C-axis length. And 5% in crystal terms is gigantic. So this was the first kind of tantalizing suggestion that something different might be happening. Okay, so let's look at this warts and all. Long story short, we discovered a different structure type in this family of materials. Okay, this is perhaps most easily recognized by looking at the electron microscopy, but it's also recognizable in the diffraction. And we can see 3 different domains in these films. We can see a projection down the 010 axis, the 100, and the 110. So these are 90 degrees relative to each other. This is 45 degrees. And if you really zoom in, you can see that one axis looks like this, so it's kind of orthorhombic, or it's, this is rectangular, whereas along the 90-degree axis, it has this tilt associated with it. Okay? And this was associated with a monoclinic phase. So the bulk is orthorhombic globally, and this was very surprising to us to see that this was a monoclinic phase. And this splitting here corresponds to the monoclinic angle. Okay, so we went back and we looked more closely at lanthanum diantimonide, and my DFT collaborators did these experiments. A little bit enigmatic for us, because if you look specifically at lanthanum, not at samarium, you can see that there are these new energy minimum at a large displacement in Y and a small displacement in X. So the previous minimum was here, and now it's slightly displaced. So in contrast to the ytterbium type or the samarium type, there's this new ytterbium type monoclinic structure, which has this very slight monoclinic shear, and the C-axis is compressed 5%. So this may sound like esoteric crystallography to you at this stage, but this actually makes a big impact on the physics, and this is where I'd like to take you soon. How am I doing for time? Yeah, maybe I can talk about this to give you a little bit of an intuition of how we think this is happening. And this is really beautiful, intuition that we've obtained from what's called the Zintel-Clem rules, which basically talk about how orbitals are filled when they violate like the octet rule, basically. So if you have too many electrons in the structure, how are they redistributed, essentially? And then in a more substantial manner, we've taken influence from Roald Hoffman, who is at Cornell and is still alive, who has done really, really amazing work talking about toy model systems of specifically antimony to outlook, and how orbital configurations and orbital filling influences the structural configurations. Okay, so antimony is here. We have 5s3, 5p3. Okay, and I can think that if I start with antimony 3-, so I take my antimony and I give it 3 extra electrons and I fill out the orbital, it's probably going to coordinate in this octahedral arrangement. This is kind of a general outcome of this 3- configuration. So it'll be configured in all directions like this. So this will probably contribute to a 3-dimensional structure. If I go to 2-, right, this is similar to like a dimer. It has 1 extra electron and a lack of an electron here. So it'll like to form these dimers with these neighboring sides. Right? This is kind of like halogens, right? And then 1-, it'll form these chenions, or alternatively, it'll form square nets. Okay, and then if you go to antimony 0, which is just regular antimony, then you can observe what the bulk crystal structure of antimony is, and it kind of looks like these ammonia atoms, which are all bonded together. So by looking at the ionization state, you can kind of make hand-waving arguments about what the configuration of the atoms are going to take within the unit cell. And this is what we did just in an intuitive way, looking at our structure and comparing to the this samarium type structure, which it's closest to. Okay. So if I were to say in this structure that lanthanum is 3+, okay, so it's giving up 3 electrons, and those 3 electrons are going somewhere. One of them is going to go into the square net, because I told you a square net needs to be 1-. And then the remaining 2 come into here, into this interlayer. So it's just redistributing charge. Okay? And if I have 2-, this would like to form dimers like this. Okay, so you get eventually some configuration where you have some interdimer distance, some RDD, so dimer, and then interdimer distance, and this is some ratio that we can come up with. Okay. Now, if I think about lanthanum 2+, which is the case of the ytterbium type structure, now I put 1 electron into this square net here, and then the other electron into here, and this would prefer to form chains now. Instead of forming these dimers, which would like to split apart, it would like to form a chain, a continuous chain. So now this R dimer over RDD is just 1 because they're all equidistant from each other. And then we can take out diffraction data, and we can match it with DFT, and we can look really locally at what our structure looks like. And we can see that this R dimer over RDD distance is somewhere in the middle of these two, which is inferring that we don't have lanthanum 2+ and we don't have lanthanum 3+. It's probably somewhere in the middle. It's like lanthanum 2.5 or something like that. Okay? So this is what we've labeled this as. And this is what kind of our hand-waving argument is, that lanthanum is now in an intermediate oxidation state, and this is facilitating this new type of, basically the interparticle or the interdimer distance, and this is modifying it and compressing the z-axis. This is also borne out in momentum space. You can learn a lot from momentum space. Maybe this hasn't, set in a lot of your minds, but you can read off oxidation states from these type of momentum space representations. For example, the blue bands here in the samarium type structure are completely empty, which would imply lanthanum doesn't have any electrons, which would imply 3+. Right? These guys are full, okay? And then the dispersing bands that you see at the chemical potential, these correspond to the 2D sheets, which are partially full. So these are your metal layers, your 2D sheets, and then you open a gap between the diamonds and lanthanum. So this is what you'd expect from 3+. But we take our structure and we do DFT, and you can see it's much more complicated. In addition to the red dispersive bands of the square net, now you in addition have the antimony from the ionic layer and the lanthanum from the ionic layer touching at the chemical potential. So this is now less of an ideal 2D system, and it's much more three-dimensional. You can actually see from what the Fermi surface looks like. It's not these two-dimensional sheets anymore. It's kind of got these three-dimensional dispersive bands. So all this to say that through fortuitous circumstances, we've taken this structure, grown it as a thin film, and it's more three-dimensional, has a different orbital filling from the bulk. Okay, that's a long-winded way to get to superconductivity. But this is really what it does. Okay, so this is superconductivity in the bulk. TC onset can be anywhere that you want to call it, maybe 1.5 Kelvin. And when it actually reaches zero resistance, it's maybe 600, 700 millikelvin. It's quite a broad transition for a bulk crystal. But this is because the layers are quite decoupled. This is a very long C-axis, and these layers are quite decoupled. Now, we have a 5% C-axis compressed crystal. This leads to a more three-dimensional coupling, and this enhances the superconductivity. It's a very sharp transition, and at 144 nanometers, we see a TC exceeding 2 Kelvin. So after all this is said and done, the hypothesis that we have is that we're actually stabilizing the high pressure phase of lanthanum diantimonite that has not been detected experimentally from a crystallographic standpoint. If we look at our rho T, you see basically a featureless rho T. And if you look in bulk, under pressure, which is the red and purple colors here, this is basically featureless. And then if you look at their superconductivity under pressure, TC is kind of about 1.8 or 2 Kelvin or so. And this is a fairly similar value to us. So this is a hand-waving link that we're making, I will admit, but it kind of walks and talks like the high pressure phase. Okay, so now let's play with the real degrees of freedom that MBE has. And that's the ability to make essentially arbitrary thicknesses quite easily. So this is a unit cell. This is about 2 nanometers. And this is the data that I showed you previously with now thinner samples added. So we can maintain superconductivity down to about 4 nanometers, which is about 2 unit cells, or 2.5 unit cells, depending on how you characterize the roughness. And 1 unit cell becomes insulated. 2 unit cells is the best we can do with this type. Okay. Unsurprising is that this becomes a very anisotropic superconductor. So this is a 2 unit cell sample where we apply a magnetic field out of plane for the blue data and then a magnetic field in plane for the blue data. They both show this type of trade-off between temperature and magnetic field. Okay, so it's fairly weak when the magnetic field is applied out of plane, as vortices readily penetrate the sample. Pardon me. But when it's very thin and you have suppressed orbital effects, this superconductivity becomes relatively robust. And this horizontal line that I have here, this is what's called the Pauli limit. This just comes out of like BCS theory, saying that if superconductivity is killed purely by Zeeman energy, this is the number. It's related to TC. We can see that this exceeds that, which is not so surprising because spin-orbit interaction is so strong. Okay, we can do Tinkham analysis, which you do for a 2D superconductor to show that this is two-dimensional. So we rotate direction of the magnetic field, follows its cusp, which is best fit by a 2D Tinkham. This is a very standard analysis. Okay. So it's a new 2D superconductor, a new family of 2D superconductors, which is highly anisotropic. That's great. What else can we do? I told you that lanthanum diantimonide exists, and I also told you that cerium diantimonide exists. Cerium is to the right of lanthanum on the periodic table. Okay. And they both take the same structure. And as a preamble to this section, you might know about these type of experiments that have been done a long time ago. this is the idea that you can take a superconductor and you can put magnetic ions in. Conveniently, this is literally lanthanum metal that they put cerium into. Lanthanum superconducts, and cerium kills the superconductivity. You can do the same with neodymium, right? And this is really beautiful physics from the 1960s, right? This was formalized by Brikasov, and these early experiments were done by Matthias. Okay, so we can dope this, and this is where nice stuff comes out. So cerium and lanthanum, this is the phase diagram. There's no intermediate phases in between the two, so lanthanum and cerium don't form compounds with each other. If there's a lanthanum site, I can put a cerium on there. Thermodynamics lets that happen, and we can show that in diffraction. So we can throw a series of samples from undoped to 5, 10, and actually since then we have 100%. So we can grow the full alloy of lanthanum to cerium dianthene. Okay, and the structure stays the same. So this is actually quite a lot of cerium. And the interesting physics happens at much lower cerium concentrations, and that's illustrated here. So we're growing 2 unit cells, 4 nanometers, and we're taking it to low temperature, and we're measuring the superconducting transition. The undoped film that I showed you previously has a TC here of about 0.7 Kelvin or so. And then I start to put in very small amounts of cerium. You can see that this is atomic percent. This is very conveniently possible in MBE because we evaporate. So we just evaporate a very, very, very small amount of cerium at the same time as lanthanum. Okay? And we can see by 0.014, it's fairly weak, and then 0.019, it's completely killed. And then 0.025, we have this upturn indicating some weak localization behavior as well. Okay? And we can parameterize this here as a function of concentration. And if you're used to seeing this, great. If not, don't worry about it. This is kind of, a digamma function, one of the special functions, and what you can describe is the relationship between TC and the undoped TC, TC naught, where this is renormalized by some value of rho, and rho is somehow related to tau, and tau is related to some scattering rate, Vs. Okay. Long story short, Vs is just some order of magnitude perturbation to the system which suppresses superconductivity. Okay, and when this Vs value gets to the order of Tc, like 1, superconductivity is destroyed. So this is what we parameterize. So this is like 0.07 Tc, 0.06, 0.09, and then when it's order of Tc, it's destroyed. So this is just some generic rate that shows up time and time again in analysis. All right, so we go from superconducting to normal by building cerium, and very interesting things then start to happen in an applied magnetic field. So this is the in-plane magnetic field only at this point in time, and this is for an undoped sample. This is very conventional behavior. We put a very small amount of cerium, and it's still fairly conventional, just suppressed. We put a little bit more cerium, and you start to see this non-monotonic behavior in TC. And then you put a critical amount of cerium, and you get this very unconventional superconducting behavior, where you cool down, and I showed you the raw data previously, it doesn't superconduct. And then you apply an in-plane field, and suddenly you get this beautiful zero-resistance superconducting state. It's characterized by this half dome, which is actually a fit to a model that I'll show you in a moment. This is what the raw data looks like. It's kind of challenging to measure because the temperatures are very low. And small angular offsets are very difficult to compensate, but we can manage that. So the blue is a zero field, and then getting towards green is about half a Tesla, where we have this nice zero resistance state, and then going to higher fields, red disappears again. So this is just characterizing this dome. Okay, so I want to talk about this phase in a very Occam's razor manner. I think it's very easy to get up and talk about like fancy p-wave, blah, 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 and coexistence of magnetism, so on and so forth. But we don't have evidence for that. So let me try to keep things in a, dare I say, Russian way. This piece of theory is Russian. So, if we look at a Cooper pair, right, we know that phase coherence is really the hallmark of superconductivity. And anything that is going to break this phase coherence is going to end up destroying the superconductivity. So If we think about some orbital effect, we have some Cooper pair here with equal and opposite momentum and opposite spin. So this is just a BCS superconductor. Right? If we apply some magnetic field out of plane, this is going to inject a Lorentz force. This is going to change the trajectory. Okay, and this is going to change the phase of these two relative electrons. And this is going to enter the total Hamiltonian here by some pair breaking, what we'll call the orbital effect, which effect suppresses the superconductivity. So this can be characterized here in terms of numbers that you actually care about. Again, Vs is just how big it is, and D is the diffusion coefficient, H is the magnetic field, and then there's some constants. Right? So you can think if I have a very mobile set of electrons, the orbital effect is going to be large. If I have a really disordered metal where diffusion is small, then the orbital effect is going to be small. So this is why disordered materials can be very resilient to magnetic fields. A similar argument can be made for the paramagnetic effect. This is just flipping the spin, right? This is like a Zeeman coupling. And again, we can parameterize this in terms of some V sub S, which now takes into account spin-orbit scattering. So instead of like real physical scattering, this is scattering off some site where the spin gets scrambled, so as it precesses. Okay, and again, H squared. So these are very conventional terms. So this is why I said before, it's not so surprising that we exceed the Pauli limit, because we have antimony and lanthanum. These are heavy elements, and spin-orbit coupling is going to be strong, right? Which makes tau spin-orbit to be a very small number. Okay, which makes this effect small. So the subtle feature here is actually the magnetic impurity scattering. So if you take anything away from today's lecture, I would hope that it's some intuitive understanding of how this magnetic impurity scattering is more complicated and more beautiful than just the orbital paramagnetic effect. So this is some, exchange, and there's some scattering process and some angular momentum. But basically, we can come up with another rate where we have some J squared, which is the exchange interactions, spin, and the number of particles. Okay. So all this to say that we have different scattering rates, and these work in some additive or subtractive way to either increase or reduce TC. This is really how you break the superconductor, by making these work either with each other or against each other. So this is the theory that I was referencing from Mikhail Feigelman, who's really one of the titans of superconductivity. If you read the literature, he's been a major contributor for decades now. And he's still active. We had a Zoom call with him about this. It's very interesting. And he came up with this model, which I won't go into all the details because it's kind of pretty complicated to solve. But basically the idea is that you have some very long expression which needs to be solved self-consistently. Okay, it has Matsubara frequencies, some energy cutoff. There's some impurity rate, scattering rate, which is the Baire rate. But then this is reduced by some delta gamma, which is related to how the spin actually evolves in temperature and magnetic field. We have the paramagnetic effect over here, where H is the real field, and then this is the spin polarization of the magnetic impurities. And then we have the orbital effect. Okay, so maybe I'll start with the orbital effect because it's the easiest. We have the Fermi momentum multiplied by the thickness. We don't know what the Fermi momentum is. This is some complicated Fermi surface, but we have like a number that we can put in that we think is order of magnitude correct. We know what D is, and this just depends on H squared. So this is always just some parabolic effect that increases in field. This always kills superconductivity, the orbital effect. The paramagnetic effect is more interesting, actually. So H is a field that we apply, right? But this can be positive or negative depending on the sign of J. So if you have ferromagnetic coupling to the spin, right, the paramagnetic effect increases and you increase the field. Whereas if you have antiferromagnetic coupling, it actually works in the opposite direction. So this is the paramagnetic effect on TC when you have antiferromagnetic coupling. So you can actually have this go through zero at some point. And this is called the Jaccarino-Peter mechanism. Okay, and then by dialing in impurity scattering, which is harder to plot in this representation, The black curves here are fits to the data. This full self-consistently solved model. Okay. I don't know what J is a priori. I'm not really sure how to measure it as well because there's so few electrons here and there's no ordering. My gut would tell me antiferromagnetic coupling because it's like a condo-like system. But for both situations, we can get a reasonable agreement between the experimental data and the black curves. This antiferromagnetic overestimates GC. Okay, but it's a really nice model because you can just break these down into energy terms, and you don't need to know anything about the microscopic details of the wave function at all. Okay, I just want to show a few pieces of literature and say that this is not an field-induced superconductivity has been seen. It has not been seen in this incarnation of extremely dilute dopants where you resolve a full superconducting dome. But in heavy fermion systems, for example, where you have an antiferromagnetic ground state that is killed by superconductivity, by a magnetic field, superconductivity has been seen to emerge at high fields. And this is related to the Jaccarino-Peters mechanism. And then in materials like amorphous lead, where you can put 10% of cerium in, there are also similar features where you can have an onset superconductivity at relatively high fields. Okay. So it's kind of it's a little bit gray as to where all of these scenarios fit into kind of this physical framework. Okay, so I'm running out of time, so I might skip that and just finally impress upon you this last feature. The orbital effect that I spoke about and the paramagnetic effect are just related to H here and H here, and there's some Brillouin function here. Okay, but inside here there's more sensitive terms on temperature and magnetic field. So the Brillouin function is a very sharp function of H and T, whereas this term here has a more complicated structure in H and T. And so basically what we plotted here in this parameter space is the ratio of this gamma, which is the reduced scattering rate, divided by the bare scattering rate. Right? So if you see blue, it means that the spin scattering is less, the magnetic impurity scattering is less, whereas if I show you red, it's at a maximum. This is basically what it boils down to. And you can see that it's quite complicated in this two-dimensional parameter space. This is why I didn't illustrate it a moment ago, because it's kind of a lot to absorb. But I can take two line cuts at either low field or high field, and I can just show you what these look like. So at low field, I have this relationship where I have to go to really, really low temperature before this scattering rate reduces. Whereas if I'm at high field, the scattering rate is already reduced dramatically. So really what is under the hood here is an orbital effect that's killing superconductivity, a paramagnetic effect that's killing superconductivity, and a fluctuating magnetic moment that's killing superconductivity. But the fluctuating moment can be suppressed either by temperature or by field. And you have to understand it in a two-dimensional parameter space really to observe that. Okay? So that may be a little bit a lot to digest, but if you want to talk about it more, I'm very happy to. Okay, so that's basically the end of the talk. I want to say that the model is for a dirty, disordered metal with an isotropic Fermi surface. Our material is not perfect, but it's not an amorphous metal. And, we've completely neglected a microscopic understanding of what does the structure endow in the band structure. This lacks inversion symmetry about the length of side. Are there exotic pairing scenarios? Are there multi-band superconductivities? And really, what is the detail of the origin of the sign of J as well? So these are things that we don't know, but perhaps we'll investigate in future iterations. So this is, most of the work here was done by Adrian. He was my heroic student that came to me during COVID and graduated 2 weeks ago. So congratulations to him, and thank you very much for your attention.
Thanks for a nice talk, Joe. Do we have questions? Yes.
So you did the in-plane magnetic field and showed that the superconducting phase is anisotropic.
Yes.
And does this anisotropy just bore out of the anisotropic lattice, or does it?
This, you mean?
No, not the Pauli limit violation, but when you rotate the in-plane magnetic field, and there's a very large peak at 0 degree.
Yeah. The Tinkham, yeah.
Yes.
This.
Yeah.
This, I mean, in a hand-waving sense, the coherence length here is extremely long. It's like 50 to 100 nanometers. And we're working in 2-unit cells. So this is like, in the strict sense of a word, a 2D superconductor.
Oh, I see.
I didn't mention what the coherence length was, but really,
right.
it's just a 2D superconductor.
You're not talking about in-plane rotational symmetry.
No, sorry. No. This is
Got it.
just a definition of in-plane versus out-of-plane field.
So if you were to rotate in-plane, do you see anisotropy too?
We haven't done that, but what I mentioned this to you before. If the crystal looks like this,
Right.
this is all well and like you do out-of-plane diffraction, and this looks magnificent. You do in-plane diffraction, it's kind of a little bit all over the shop. So you have 0, 90 degrees, and 45-degree domains in the crystal. So I don't really know what you'd get out of that. But if we could suppress that, it'd be great. One thing that we're trying to do is grow an A-plane sapphire. And that just has a rectangular structural motif. And there's kind of an indication that we can reduce the amount of twins, but it's not perfect yet. Kind of take what you can get.
Other questions? Okay.
So in the field stabilized phase, did you look for the superconducting diode effect? Or is it?
No, we haven't done any of these fancy things yet.
Okay.
I'm sorry, like these. I know you live in Austin. The answer is
You should
no.
have.
We haven't done any current dependence.
Okay.
To begin with, these are very low temperatures. I don't know how comfortable I feel about doing current dependence at that low temperature. Especially, your wires have resistors in there. What's a temperature effect, what's not. I kind of feel a little bit uneasy about that.
There's only one way to find out.
There's only one way to find out. This is correct. Unfortunately, he was just so keen to graduate. His defense, he has 2 kids, so he kind of really wanted to earn money.
Other questions? I was just wondering, you were saying at some point that you think you are like stabilizing that
The high pressure phase?
the high pressure phase.
Yeah.
The high pressure phase though, that's like isotropic pressure, right? To some extent.
Yeah. So
And
when
here
I'm
ZX is
Compressed.
5% compressed.
Yeah.
What about the A and B? I mean,
so the total volume is less than the bulk phase.
Mhm.
I don't know if I have the A and B axis parameters ready to go, but the total volume is certainly less.
Mhm. Okay.
Which would suggest it's emulating hydrostatic pressure. But yeah, this is a very kind of question mark slide. This is the best hypothesis that we can come up with. But I would love to see actual diffraction from bulk.
All right.
People suggest that I do it. It's not my problem.
And the 2D analysis, doesn't it hold for different thicknesses or like?
Like a schist plot?
Yeah.
Yeah, so we haven't done it extensively, but we've done it, I think, for up to 12 nanometers, and they all follow a 2D Tinkham.
Yeah. Okay.
But even for the thickest film, here the coherence length is like 200 nanometers.
Mm-hmm.
So whether or not it perfectly conforms, I'm not sure. But yeah, I mean, for this series of samples from that, coherence length versus thickness argument, it seems like they're all 2D.
Any other question? Yeah, go ahead.
Maybe it's more of a comment that at 4 nanometer, that's 2-unit cell.
Yeah.
I don't think I've ever seen such a sharp transition in any material.
It's very interesting, isn't it?
So how big is your sample?
It's
Size.
3 to 4 millimeters square.
Oh my goodness. Okay. Do you have any thought as to how do you stabilize such long range order in terms of a uniform sample? Like how can you you're counting atoms? You're putting several layers of atoms on there. How can it be so uniform?
I mean, MB is made to be uniform on inch scales. This is the trick of the tool. That's probably, the most evasive answer that I can give. But yeah, no, it's surprising. I mean, we've like fit these. I've forgotten what the functions are called. But like, you can fit these curvatures and stuff of the transitions. They don't fit that well. So I think there's probably interesting physics happening just in the transition itself.
Like the Halpern Nelson fit at the outside.
Yeah, exactly. I think it was that. No questions from students? Good or bad question? There's no such thing as a bad question.
Okay.
All right.
Maybe we can end it here, and thank Joe again for the nice talk.
Thank you.